Hey, good morning, class, and welcome to our third day of online learning. Today's goal is to rewrite rational expressions to transform functions from the form of ax plus b over x minus c to more of a transformation form. Now, what we want to start by understanding is in this form of ax plus b all over x minus c, this is more of a rational expression. And it has its advantages in that form, but it's also a little bit harder to really graph without the use of a calculator. If we write it into a transformed expression, we know from our previous work that the h is going to represent a horizontal shift and the k is going to represent a vertical shift. So we want to keep those things in mind as we go through this lesson. Let's begin this lesson by reviewing the parent function of y equaling 1 over x. In green, you'll see the graph of y equaling 1 over x. And if we were to make a table for this type of function, and we choose just values in the first quadrant, if x is 0, y is going to be undefined. If x is 1/2, then if x is 1/2, then 1 over 1/2 is 2. If x is 1, 1 over 1 is 1. If x is 5, 1 over 5 is 1/5. So you get this hyperbolic type shape, or this half of a hyperbola here in green. You'd get a similar graph if you were to choose x being less than 0. So what are the domain, range, asymptotes, and end behavior, all topics that we've discussed in previous math classes? Well, our domain is going to be all reals for x except for where it's undefined. And that's what gives us that vertical asymptote in that red line right there. And our range is all reals except y cannot be 0. It's impossible to have an output. You have 1 over x. It's impossible to get an output of 0. Therefore, those values lead to our two asymptotes. We have a vertical asymptote at x equaling 0 and a horizontal asymptote at y equaling 0. End behavior. As x gets larger in a positive sense, in other words, as x is going from 0 to 1/2 to 1 to 5, that y value keeps getting smaller and smaller. And it's going to go towards 0, but doesn't quite ever get there. And as x goes in a negative direction, as x goes from 0 to a negative 1/2, negative 1, negative 5, y is also going to go to 0. So if we use that equation, 1 over x, and then take a look at a graph of 1 plus 1 over x plus 2 plus 3, what we're really doing is we are taking f of x equaling 1 over x, and we are going to create two transformations. We're really going to be shifting this 2 to the left, so horizontal shift of 2 left, and a vertical shift of 3 up. That means my vertical asymptote and horizontal asymptotes will shift the same amount. The vertical asymptote used to be on the y-axis right here. That's going to be shifted 2 to the left. So I now have a vertical asymptote at x equaling a -2, and a horizontal asymptote is going to be moved up 3. So 1, 2, and that's at y equaling 3. Let's get that a little bit better. Y equaling 3. Now for the domain is going to be all reals, so x is an element of the reals, except x cannot equal that -2. In the range, y is going to be an element of the reals, but y cannot equal 3. My asymptotes, well, I've already listed those. That's at x equaling a -2 and y equaling 3. The end behavior as x goes to positive infinity and as x goes to negative infinity, what's going to happen to my graph? Well, this is just a shift of 1 over x, 2 to the left and up 3. So the graph really looks pretty much the same as the green graph on the previous page. Just with that shift. So as x goes to positive infinity, that y is getting closer and closer to 3. As x goes to negative infinity, y is getting closer and closer to 3. So the equation for the end behavior is just y equaling 3. So some rational functions look complicated but are simply shifts of f of x equaling 1 over x. So in problem 51 here, we want to use polynomial division, which can be your long division or area model, to rewrite 3x plus 7 over x plus 2 into a transformed rational expression. We want to get this to be in the form of y equaling 1 over x minus h plus k. So if I use my area model, I have x plus 2. I'm going to divide that into 3x plus 7. Put my 3x up there. 3 times x is 3x. 3 times 2 is 6. 1 plus 6 is 7. So my equation, h of x, is really 3 plus, I have a remainder of 1, over x plus 2. Or some of you might rather look at it as 1 over x plus 2 plus 3. And that's exactly the same equation that we had on the previous page. So what are the x-intercepts and what are the asymptotes? Well, those x-intercepts occur when y is 0. So I want to find some x value when y is 0. My y-intercepts, or intercept, occurs when x is 0, and I need to find the corresponding y value. So let's start by plugging 0 in for y. 0 equals 3x plus 7 over x plus 2. Now in order for a rational expression to equal 0, the numerator has to equal 0. So I'm going to take 3x plus 7, set that equal to 0, and solve for x. Subtract 7, divide by 3, and I get x equaling a negative 7/3. So the x-intercept, if I can get this to erase, so my x-intercept happens to be a negative 7/3, 0. Now, for my y-intercept, that occurs when x is 0. So I'm going to take h of x, or let's just call it y equaling 3 times 0 plus 7 over 0 plus 2, which comes out to be 7/2. So my y-intercept is going to be 0, 7/2. The rational expression form that we have in part A is oftentimes going to be easier to use when you want to find your x and y intercepts, whereas our transformation form of the equation that we have right here in yellow, that's going to be easier to help you find your vertical and horizontal asymptotes. So what I would recommend doing is taking a look at that form of h of x equaling 1 over x plus 2 plus 3. And if we talk about our transformations, this was our transformation of 2 to the left, which means it's going to move that vertical asymptote to the left. Meaning our equation for the vertical asymptote is now x equaling a negative 2. The plus 3 is moving your horizontal asymptote up 3. So the equation for the horizontal asymptote is now y equaling 3. So the takeaway from this page is that the transformed equation is going to help you find your vertical and horizontal asymptotes, while the rational expression equation is going to help you find your x and y intercepts. Now, I know I've been spending some time in the past Algebra 2 course and some of the Pre-Calc course working on long division. A couple of you may even know synthetic division. All of you know the Polydoku division. Sometimes there are faster ways to write or to divide rational expressions, and this just happens to be one of them here. We want to write 20/17 as a mixed number. If I was to go back and do division from elementary or middle school, I would get 1 and 3/17 because 17 goes into 20 one time and 3 is left over. Najma wants to rewrite the fraction by using a giant 1. So she's going to take that 20/17 and she's going to split that in the numerator of 20 and split that into 17 plus 3. Using her fraction skills, 17 plus 3 over 17 is the same as 17 over 17 plus 3 over 17, which is really just 1 plus 3/17. That is an equivalent expression to 1 and 3/17, because 1 and 3/17, this and really does mean to add. So if I want to illustrate this approach with 19/17, well, 19 is 7 plus 7 plus 5 over 7, or 2 times 7 plus 5 over 7, which is 2 times 7 over 7 plus 5, which is, plus 5 over 7, which is really just 2 plus 5/7. Now, can we use this skill here to actually perform division? Now I'm going to take x plus 3 divided by x plus 1. My numerator of x plus 3 is x plus 1 plus 2. I've taken that 3 and split it into a 1 plus 2 over x plus 1. If I group the x plus 1, I can rewrite this as x plus 1 over x plus 1 plus 2 over x plus 1, which becomes 1 plus 2 over x plus 1, which really is now my rational expression in a transformed state, where I can identify a horizontal shift of 1 to the left and a vertical shift of 1 up. What I'd like you to do is take a minute, pause this, and see if you can rewrite h of x in a transformed as a transformed function. When you're done with that, resume play so you can see the answer. Hopefully you were able to take a minute or so, a couple of minutes, to rewrite this as in a transformed equation. The 3x plus 7, I'm going to rewrite that as x plus 2 plus x plus 2 plus x plus 3. And I have 2 x plus 2's, and then the x plus 3 is going to end up being my remainder. So this simplifies then into 2 over x plus 2 times x plus 2 over x plus 2 plus x plus 3 over x plus 2, and that simplifies to 2 plus x plus 3 over x plus 2. If you think you got the hang of it at this point, then what we'd like you to do is go back to the Canvas page or go to your assignments and complete the 4.2.1 assignment and the 4.2.1 exit slip. If you'd like some more practice, then go into the next page and we will do one more problem. What I'd like you to do is consider the function of k of x equaling 2x minus 5 over x minus 3. We're going to use polynomial division or Navier method to rewrite k of x in the transformed state. We're going to then identify the x-intercepts, the asymptotes, make a graph, and describe the end behavior. What I'd like you to do is pause this and go through A, B, and C and see what you come up with. And then come back and play to check your work. If I'm going to use Najma's method, then k of x is going to equal x minus 3 plus x minus 3 plus, now that minus 3 and minus 3 is actually minus 6, but I only have a minus 5 up here, so I'm going to go plus 1 over x minus 3, which is equal to 2 x minus 3's plus 1 all over x minus 3, which would be equal to 2 times x minus 3 over x minus 3 plus 1 over x minus 3, which means k of x is equal to 2 plus 1 over x minus 3. Since I have this in my as a transformed equation, I'm going to look at my two shifts. My vertical shift is up to, oops, I deleted that, and my horizontal shift is going to be right 3. This also then leads to my asymptotes. This is going to lead to y equaling 2 as my vertical asymptote. And this is going to lead to x equaling 3 as my actual vertical. Let me change this to horizontal. And x equaling 3 is my vertical asymptote. What about the x-intercepts? Well, let's use the rational expression form. One minute here. So x-intercept is going to be at some value, comma 0. My y-intercept is going to be at 0, comma some value. So what x value can I plug in that's going to take 2x minus 5 over x minus 3 and give us an output of 0? That only occurs when the numerator equals 0. So 2x minus 5 equaling 0. Add 5 to both sides. Divide by 2. X comes out to be 5/2. So my x-intercept is 5/2, comma 0. And to find the y-intercept, I'm going to plug 0 in for x. So 2 times 0 minus 5 over 0 minus 3. That's going to come out to be a negative 5 over a negative 3, or a positive 5/3. So my y-intercept is 0, comma 5/3. Now I'm starting to run out a little bit of room here, so we're going to expand this like I did and see if we can sketch a graph off to the side here. My vertical asymptote happens to be at 3. So 1, 2, 3, 4, 5. 1, 2, 3, 4, negative 5. 2, 3, 4, positive 5. 1, 2, 3, 4, negative 5. So at 3, I have a vertical asymptote. And my horizontal is at a positive 2. And now it's just a transformation of that equation, y equaling 1 over x. So my graph is going to look something similar to that. And that end behavior, as x goes to positive infinity, as x goes to negative infinity, y is going to go to that horizontal asymptote of 2. Y goes to 2. Hopefully you enjoyed the lesson for today. Again, there is a homework assignment and an exit slip on the 4.2.1 page, or you can check your assignments in Canvas. Everybody, we wish you a great day, and we will talk to you during office hours, and we will have another video for you tomorrow.